Hello, hello, hello. This is Coach Ikram, and welcome to this video on the periodic table of the elements. In this video, we're going to be discussing periodic trends. So there's a lot of trends that we can study on the periodic table, and most of them are going to be governed by two electrical phenomena. The first is going to be Z-effective nuclear charge, and the second one is going to be shielding. So breaking those down, Z-effective nuclear charge. It is the overall force that the protons in a nucleus are going to exert on the surrounding electrons. Remember, protons are positively charged, electrons are negatively charged. There's going to be a force there. In an energy level, in any given energy level, the electrons in that energy level are going to be attracted to the nucleus equally, regardless of how many electrons are there. So Z-effective nuclear charge overall is going to be influenced by the atomic number. And it's also going to be influenced by electron repulsion. So electrons, remember, will repel each other because they're all negatively charged. So as you move across a period in the periodic table, you're going to note, like, as you add a proton every single time, more protons means you're going to increase the Z-effective nuclear charge because your positive charge in that nucleus is increasing. So it's going to have more of a force, a pull force on those electrons around it. Shielding, the other phenomena that's going to account for most of the trends, is the addition of entire energy levels between the protons in the nucleus and the valence shell of electrons. So if you think about it kind of in a very basic form, if you've got your nucleus and if you add energy levels, as you add the energy levels, the electrons that are out here are going to be shielded from the nucleus by all of these levels in the middle. And this is going to be the shielding. And again, this is a very rudimentary picture, but it gives you kind of the basic idea. Regardless of nuclear charge, entire energy levels worth of electrons will greatly increase the distance between the nucleus and the valence shell. As they increase that distance, it's going to reduce attraction. And then remember, electrons are going to repel, and that's going to further increase the distance. So the first trend that we're going to talk about is atomic radius. It's the radius of an atom. It's going to be measured in picometers or angstroms. And this is the unit for that. It's 1 × 10⁻12 meters. It's going to be measured indirectly from center to center of an atom, because we can only see electron clouds. We can't actually see the radius. So it's going to be measured from the middle here straight over here. So atomic radius as a trend, if you are moving left to right across the period, you're going to be increasing the Z-effective nuclear charge. So for each element that you move across, if you start on the left and you move across to the right, one proton is going to be added to the nucleus and one electron is going to be added to the valence energy shell, or valence energy level. As you add a proton, as you move across, the more protons that you have, it increases your Z-effective nuclear charge, which means those electrons are going to be pulled in closer to that nucleus because there's more of a force, there's more protons there that has more of a positive charge on those electrons. So to continue on this periodic trend, remember, like I just said, nuclear charge is going to increase as you move across because every proton you add makes the nucleus more positive, and that's going to pull the electrons inward. So looking at this practice, we have potassium and krypton. Looking at your periodic table, potassium and krypton are on the same energy level. Potassium is an alkaline metal, and krypton's over here as a noble gas. They're on the same energy level, but as you move across that energy level, you're adding more protons. Therefore, you're increasing the Z-effective nuclear charge. So those electrons are getting pulled closer to the nucleus, which is making the atom smaller and making the atomic radius smaller as you move towards krypton. So potassium is going to have the larger atomic radius. If you're looking at atomic radius as a group trend, so you're looking within a group from top to bottom, atomic number increases as you go down a group. So atomic radius is going to increase. Because as you go down a group here, your nuclear charge is going to increase. That's true. But shielding is the most important effect that you have when you move down a group, because as you go down the group, you're adding an energy level. And as you add those energy levels, those electrons on those outer energy levels get further and further away from the nucleus. So the pull of those protons on those electrons is not going to be as strong the further you get out. So it keeps the atom from getting smaller. Instead, it's going to be getting larger as you go down a group. So shielding, as energy levels are added, electrons are less affected by the pull of the positively charged nucleus. So as practice, barium and magnesium, which one has the larger atomic radius? So if you look over here, barium is down here and magnesium's here. They're in the same group. They're both alkaline earth metals. But barium is going to be larger because there's more energy levels between those outer electrons and the nucleus. And there's also more electrons. And remember, electrons are going to repel each other as well. And so magnesium is going to be smaller, and therefore barium will have the larger atomic radius. So this is an overall look at the periodic table and the atomic radii of each of the atoms. And so you can see, if you look at it, the overall trend as you move across the period, the effective nuclear charge causes your atoms to be smaller. And as you move down a group, the shielding is causing those electrons to be larger. So the next trend that we're going to talk about is first ionization energy. This is going to be, as by definition, the energy that's required to remove the outermost electron from an atom, and it's going to be measured in kilojoules per mole. So if you're looking at it across a row or across a period, as your atomic number increases, the ionization energy is going to increase because the increasing nuclear charge holds electrons with greater force. So this is where the effective nuclear charge comes into play. Nuclear charge goes up, electrons are going to be held more closely to the nucleus. Therefore, the energy required to take them away is going to be larger. So looking at an example of first ionization energy, we're going to practice with calcium and bromine. Calcium is right here, and bromine is right here. They're both on energy level 4. Calcium is going to have a much, much lower ionization energy, first ionization energy, than bromine. Bromine, right here, it's affected by that Z effective nuclear charge. There's a lot of protons on this particular energy level holding those electrons closely. It is not going to want to lose those electrons, whereas calcium has a much less Z effective nuclear charge than bromine, so it'll be able to lose electrons more effectively, which is why calcium as an ion, eventually becomes calcium ion. It does lose electrons, and bromine does not lose electrons. It will want to add an electron. So if you're looking at first ionization energy within a group, down a column, as your atomic number increases, ionization energy is going to decrease because of shielding. The further you are from the nucleus, the more easily that electron is going to be removed because it's got less of a pull from those protons because of all the shielding between them. So as a practice, sodium and cesium, if you look in your periodic table, we don't have a picture of it here, but sodium is higher in the group than cesium is. So sodium, those electrons are going to be less likely to be removed than cesium's because cesium has so much shielding. So the higher ionization energy, the more energy that's going to be required is going to be sodium. It takes more energy to pull an electron away from sodium because of less shielding than cesium. Okay, so now we're going to talk about what's called second ionization energy. If first ionization energy is the energy required to remove that first electron, second ionization energy is going to be the energy required to remove the next electron, and that would go on in successive order. So you could remove each electron from an atom. So remember, removing a core electron is going to require significantly more energy than removing a valence electron. So we're mainly talking about valence electrons here. So if you look at it, lithium, it's an alkaline metal, so its first ionization energy is pretty low. It's going to be able to lose that electron pretty easily, but once it loses that first electron, it's got a full octet. Lithium typically becomes +1. So once it loses it, that second ionization energy is incredibly high. Look at the difference in those two numbers right here. And that's because it does not want to lose that second electron. The energy required to pull it off is exponentially bigger. Beryllium then normally becomes 2+. And if you look at it, the first ionization energy, fairly low. Doesn't take a lot of energy to pull that off. The second ionization energy, also fairly low. The third ionization energy, though, you notice jumps up dramatically to 14,000. And that's because once it loses those 2 electrons, it does not want to lose any more. Okay? And if you looked over here, we've got these core electrons. Anything that's a core electron, those are going to be significantly harder to remove than valence electrons because they're core electrons. So if you notice the numbers, the energy levels required to remove them are extremely high. Electronegativity. Electronegativity is the measure of an atom's ability to pull on another atom's electrons while they are bonded. It's going to be abbreviated EN, and there's no units. Typically, you've got electronegativity difference in a bond of greater than 1.7. It's going to indicate ionic bonding. That means you have a very large difference in electronegativity. If you've got electronegativity difference less than 1.7, it's going to generally indicate covalent bonding. So it's not going to form ions. Instead, they're going to share. If you're looking at electronegativity across the period, as you increase your atomic number and you move left to right across the period, the electronegativity is going to increase. That means your nuclear charge is also going to increase. Because as you go across and you add protons, moving across the periodic table, it's going to hold on to those electrons. And when you bond any of these atoms with something else, these atoms over here, typically on the right-hand side of the periodic table, when they're bonded with something else, they are going to have more pull on the electrons in the bond than the other atom that they are bonded with. So electronegativity down a column. As your atomic number increases and you move down a group, the electronegativity is going to decrease, and this is because of shielding. The elements at the top of a group, remember, are going to have electrons that are very closely held by the nucleus because they're closest to the nucleus. And the elements at the bottom of the group are going to have more distance between that nucleus and that outer electron. So therefore, they're going to have less electronegativity once they're bonded, less pull on those electrons that they're bonded with. So looking at it overall, as you're looking at a group, the atoms down at the bottom of a group are going to have more shielding. Therefore, that nucleus is going to have less pull on those outermost electrons, and it's not going to have as much pull on the electrons once they're bonded. Reactivity refers to how likely an atom is to react with other substances. This is going to be dependent on how easily electrons can be removed, ionization energy, or how easy atoms grab electrons or pull electrons in a bond, and that's going to be electronegativity. Breaking down reactivity into metals and nonmetals. Metals, remember, have a very low ionization energy. As you move across a period and you increase that atomic number, your reactivity for metals is going to decrease. And as you move down a group, your reactivity and your atomic number increases. Your reactivity as a metal is going to increase. Why? This is because if the ionization energy is low, an atom is more likely to lose an electron, which is going to result in a chemical reaction with another atom. If you've got nonmetals, nonmetals have a very, very high electronegativity. That means when they're bonded, they're going to have more pull on electrons. As you increase your atomic number, your reactivity is going to increase. Your nonmetals are going to be, their reactivity is going to increase. As you move down a group, the atomic number increases, your reactivity will decrease. If your electronegativity is high, the atom's going to take or pull electrons from other atoms more easily when they're in a bond. It's a better way of putting it, which is going to result in a chemical reaction. So if you're looking at it overall in the periodic table, your metals, which are on this side of the periodic table over here, metallic character is going to be higher down here because francium has lots of shielding, so it can easily lose those electrons, which metals want to do. They want to lose their electrons and become cations. And they also don't have a very high Z effective nuclear charge over here because they don't, across the energy level, they don't have as many protons. If you're looking at this side, these nonmetals want to become anions. They have very high electronegativity. They pull the electrons closer to them. And they also have very high ionization energies because they don't want to lose electrons. They want to gain them. So metallic character overall as a trend, based on what we just said, these elements down here are going to have higher metallic character than these, which should make sense. These on this side are metals, and on the left, and then on the right-hand side, these are going to be your non-metals. They're not going to act in a way that metals would. So that is the end of the video on periodic trends. Please rewatch, take detailed notes, and be ready to ask questions in class.